All right, let's continue our discussion of sheaves of modules. So with sheaves of modules, most of the things that you can do with modules in commutative algebra, there's some analog of them for sheaves of modules. So the first thing we're going to talk about today is the kernel. We'll talk about the kernel sheaf. So let's let f from f to g be a morphism of sheaves on x. And remember last time we said if whenever I say sheaves on x, where x is a scheme here, I really mean a sheaf of modules. And let's try and define the kernel sheaf. Okay, so if I want to say what a sheaf is, I have to say what it is on each open set. So the kernel of f on an open set U, how will I define that? Well, I'll just look at f of u to g of u. This is the map given by f. And then I'll just have the sections of the kernel of f on u to just be the kernel of this map. All right, so and that's the definition of the kernel. You just take the kernel of f right here. Remember, f of u is an OXU module, g of u is an OXU module, so you take the kernel as a map of OXU modules, and then the kernel, and that will be an OXU module itself. Okay, sheaves also have to have restriction maps, so let's make sure that that makes sense here. If I take a smaller open set V, I'll have restriction maps here. And I'll have f right here, and I'll have the kernel f v like this. Okay, and the question is there a map from a restriction map from the kernel f at u and the kernel f at v? And this is true just by properties of the kernel, right? So if you start here and go all the way. Sorry, let me say this here. If we go like this, then you know that this composition here has to be 0. Why? Because it's the same as this composition here. This has to be 0 because it goes through the kernel. And okay, and so if you have a map from f of v to g of v, the composition is 0, then it has to factor through the kernel. That's the universal property of the kernel. Okay, so that's good. All right, so far what we've done is we've showed that the kernel is a pre-sheaf. But we'd really like to see that it's actually a sheaf. So in fact, it is a sheaf. So how do we see that? So let's let UI be an open cover of U. And let's let a phi be in a kernel F on UI. Okay, now we want to show that these phi is glued to a section of kernel F of U. Now, kernel F of UI is a subset, or it's a submodule of F of UI, right? Because the kernel is a submodule. Okay, and so so we do know that the phi glue to some section phi of F of U, right? Just because F itself is the sheaf, right? F is a sheaf. But the thing we need to check is we need to check that that phi is actually in the kernel, right? In other words, we just need to check that fu applied to phi equals 0. Okay, so that's what we need to check. Okay, but we can check this because G is a sheaf. We can check this locally, right? So we'll have f u phi restricted to ui. Well, this is just the same as f ui of phi restricted to ui. Right, because f is compatible with restrictions, and this is just f ui of phi, and this is 0 by hypothesis because of phi is in the kernel. All right, so there we go. Fu of phi is 0 when restricted to every set in an open cover. So that means that Fu of phi equals 0 once again by the sheaf property. So this is because G is a sheaf. Okay, so we have that the kernel sheaf is a sheaf. All right, let's try and do the same thing for the image. Now it turns out it's not going to work out quite as well. So we're just going to now define an image pre-sheaf, and then we'll say later how to make it into a sheaf. All right, so the image pre-sheaf we're going to find to be image prime of f, standing for the fact that later on we're going to reserve im to mean that image sheaf, which we'll define later. So the image pre-sheaf is just a thing that you expected. Is the image of this map here on each open set U. Okay, and it's easy to see by basically the same ways we did before with the kernels, or in an analogous way, that this forms a pre-sheaf. You can figure out what the restriction maps are. All right, but it turns out it's not a sheaf in general. Let me give the example that textbook gives to see why this doesn't work. All right, so here's the setup. We are going to take I to be the inclusion from A1 to A2 that just includes the x-axis x1 maps to x1 comma 0. You can see that over here as the orange line included into the black A2 over here. Okay, and then we'll define some open subsets. X1 or U1 will just be the place where x1 is not equal to 0. U2 is the place where x2 is not equal to 0. So I tried to sketch that here. These blue lines tell you that everything on this side and everything on this side are included in U1, but not the y-axis here. And then this side here is purple for U2, and this side is purple for U2, but not the orange line here. Okay, so that's kind of the setup. Let's look at the sheaf, or let's look at the map. F, which is going to be defined to be just the pullback map from OA2 to the push forward of OA1. Okay, so remember we defined the push forward sheaf last time, and we also talked about how morphisms of schemes give a map from the sheaf in the target to the push forward of the sheaf in the source, and that's exactly what's going on in here. And remember, this is just restriction, so it takes a regular function on affine space A2 and restricts it to the line here. But because of this push forward, we're viewing the restriction now as a sheaf on A2. Okay, so that's what we're doing here. Let's look at the open subset U, which is A2 minus the origin, which is the same as U1 union. Well, has an open cover by U1 and U2. And we'll see that things don't glue the way that we want to on this set. All right, so now we've got to do a lot of computations, but none of them are hard. So let's look at OA2 of U1. That will just be the polynomial ring localized to x1, right? Because x1 is not equal to 0. Let's look at it on U2. Will be the same thing. And then let's look at the intersection. In that case, you have to localize both x1 and x2. So or you can just say x1 times x2. And then finally on all of U, I think we saw early in this class that every regular function is defined everywhere except for a single point, or defined everywhere except for on a set of codimension 2 or greater is actually a regular function. So this is the whole polynomial. All right, let's look at the push forward sheaves now. So let's look at this on U1. So remember, let's look at U1 right here. We're kind of restricting this down to this A1 here. So that's just going to be x1 localized, kx1 localized to x1. So it's just going to be all the functions that don't vanish at the origin, right? Or sorry, what I meant to say is it's the rational functions that are well defined away from the origin. All right, let's look at the push forward sheaf of OA1 on U2. Now this is just going to be 0, right? Because U2 doesn't even intersect this A1, right? So there's no functions that restrict that way. Okay, and the same thing. This is an even smaller set. So this will also be 0. And then let's look at this one. This will be kx1. And what are the maps here? I mean, then the maps here are just to set x2 equals 0, right? I mean, it's exactly corresponding to this function here. Okay, sorry, and right here I should have said kx1 is this is localized to x1, right? Because the set U does not contain the origin. Okay, and once again, this map is to set x2 equal to 0. These maps here just end up, these ones are just the 0 maps because they're mapping to the 0 module, so there's nothing interesting there. So the problem is you're trying to set x2 equal to 0, but you localized it at x2, so okay, there you go. But now we need to look at the image of these things, right? So what's the image sheaf, or the image pre-sheaf? Okay, well, can you see what the image here? Well, this is clearly going to be surjective, right? So this will just be all of kx1 localized to x1. How about the image here? Okay, well, it's the 0 map into the 0 module, so nothing interesting happening here. 0. This one will also be 0. What about the image here? Well, this here is the whole polynomial ring, and when you map it into here, you're just going to get the polynomials. You're not going to get the fractions with x1s in the denominator. So this is just going to be kx1. All right, so that's what we get, and now we can see where the contradiction comes from. We have 1, for example, 1 over x, and so this is in the image pre-sheaf of U1, right, over here, and we could take a 0 in the image prime of U2, right? These two agree on the intersection. Okay, the intersection, the ring is right here, so they both restrict to 0. All right, so they kind of agree for a trivial reason. Okay, but they don't paste together. To a section of image prime of U. Why not? Well, the image prime of U is just the polynomial ring, and if these glued together, there'd be something in this polynomial ring that when you restricted it to U1, you'd get 1 over x. But of course that can't happen, right? The restriction map from here to here is just the kind of obvious inclusion. So you would never be able to get a fraction like 1 over x. Okay, so that was kind of a lot of writing, but the point of that is to show that the image pre-sheaf is not a sheaf in general. Now, basically the same thing happens with tensor products. So if I want to form the tensor pre-sheaf, the sort of obvious definition that you want to use is something like this. F tensor, let's do tensor prime because we'll define a different tensor product that's actually a sheaf later. But the tensor prime, the thing that you want to define, would be like this. You just take f of u as an OXU module, and you tensor over OXU with g of u. Okay, so that seems to make perfect sense. But let's see why it's not a sheaf. So, for example, if we have x be p1, and let's use the twisting sheaves OP1 of 1, and let's take the tensor product pre-sheaf with OP1 of minus 1. Okay, and we'll take the open subsets UI to be the sets where xi is not equal to 0 in P1. And remember that this is for I equals 1, 2, and that gives you an open cover, or maybe let's say 0, 1. That gives you an open cover of P1. All right, and then let's define let's take two sections here. Let's take x0 a tensor 1 over x0, and this will be in the tensor prime of u0. Okay, so let's remind ourselves what these twisting sheaves are. These are polynomials of total degree, rational functions of total degree 1, and rational functions of total degree minus 1. So this makes sense here. The thing you have to be careful of, you can't divide by something unless it's well defined. But on u0, x0 is non-zero, so this is allowed. Okay, and let's also look at x1 tensor 1 over x1, and this will be in f tensor prime g of u1. Okay, and kind of looking at these, it kind of looks like they should sort of be the same, right? Somehow the x0 should cancel out and the x1 should cancel out, and in fact they do agree on overlap. So let's look at the overlap. u0 intersect u1, then we'll have that x0 tensor 1 over x0 is equal to x1 over x0 times x0 tensor x0 over x1 times 1 over x0. Okay, why is this equal? Well, this thing here is just an element of this is an element of OX of u0 intersect u1, right? And this over here is also, and these two are inverses. And remember that this tensor product, this is a tensor product over OX of u0 intersect u1. So if you have a tensor product and then you multiply by some unit and its inverse unit here and some inverse here, where these things are in the ring that you're tensoring over, then that's okay. You still get the same answer, right? You can move this over here and cancel it out. Okay, but of course then this is just equal to x1 tensor 1 over x1. All right. So the point is these two things that we defined here, these are glued to a section on P1, or rather, I should say they would glue to the section if it were a sheaf. But let's look at the global sections. So OP1 of 1 tensor OP1 of minus 1 on the whole space P1. Well, okay, OP1 1 of P1, it will just be this tensor product, right? So we'll tensor over OP1 of P1, the global functions, 10 times but if you remember last time, we said that the negative twisting sheaves have no global sections. So this here is just equal to 0. All right, so this tensor product is equal to 0, but you know, clearly these things up here are not 0. Okay, so we have these sections here, but they can't glue to a global section of this sheaf. So somehow this tensor product sheaf doesn't have enough sections. It's missing the things that they should have had in here by gluing those together. All right, so the point of that example is, that in general, F tensor G, if you just take the naive thing that we defined, this is not a sheaf. It's only a pre-sheaf. All right, so there's a solution to these problems called sheafification. So we write a sheafification. Okay, and I'll write down the definition, and it'll look very similar to what we did to define the structure sheaf on a scheme. All right, so let's let F prime be a pre-sheaf. On a scheme X, and let's set F of U to be the set of all things phi, where phi is a collection of elements of phi p for every point in our open set U, such that each phi p is an element of the stock of the pre-sheaf, and for all p, there's a neighborhood UP of P in U, and a section of the pre-sheaf in over that neighborhood with phi q equal to SQ for all Q in the neighborhood. All right, so in other words, F of U is just all the things that are locally given by sections of F prime, right? Okay, so let me say that one more time. So F, the sections of F are just locally sections of F prime. So this sort of automatically makes F into a sheaf, right? So you can sort of, the gluing is sort of built into the definition. So F is sheaf instead of a pre-sheaf. And so as an example that we've already seen, so if we define, so let's say that X is a affine variety. Let's define the pre-sheaf, the pre-structure sheaf of X to be all functions phi from U to K, such that phi is equal to F divided by G for some F and G in the coordinate ring. Okay, at least on U. All right, so we already saw that this is not a sheaf in general. You know, we had some examples that were not unique factorization domains. That's what gave us the problems. Okay, so what we did is we gave a different definition that said that we need functions only to be regular functions to only locally be quotients of polynomials. So so OX is exactly the sheafification of this thing that I just defined. All right, so we've already seen this before in that situation. If we look back at our example up here, we saw that the tensor product. Sorry, I should have put a little prime here. This tensor product, this pre-sheaf tensor product here, had 0 sections, but in fact, the sheafification of this tensor product has a section. What section is it? Well, it's just given by this thing on U0, and it's given by this on U1, and then sort of by definition of the sheafification, we know they agree on the overlap, so by definition of the sheafification, they have to glue together into a section, and so it has a section. All right. So in fact, I'm not sure if when we're going to prove it, if we're going to prove it in this class, but it is true that if you take O1 tensor O minus 1, so we'll define without the prime to be the sheafification of the tensor product with the prime. It turns out to be isomorphic to O. You just add these numbers. 1 plus minus 1 is 0. Okay. All right, so here's an important remark. The sheafification has a morphism, or rather the pre-sheaf has a morphism to its sheafification. Okay, and it's not too hard to see what it is, right? It's just sort of the obvious map here. If you have a section of the pre-sheaf, then that, of course, is something that's locally given by sections of the pre-sheaf. So that's easy. I mean, or maybe you like to write it like this: S maps to SP for every P in U. Okay, and here's the lemma about this. So for all points of X, we have FP isomorphic to F prime of P. So the sheafification does not change the stocks. Okay, and this isomorphism is induced by this map that we talked about up here. And then part B is that if you start with a pre-sheaf that's actually already a sheaf, so if F prime is a sheaf, then F is isomorphic to F prime. So if you try to sheafify a sheaf, then nothing changes. Okay, and once again, the isomorphism will be given by this map that we talked about. All right, so I think maybe I'll skip the proof of this one. It's not too hard, I think, and I think this is a pretty believable lemma. Let me instead give you this exercise. I'll probably assign as an exercise, but I think it's a useful observation here. So it's a universal property for sheafification. So let's let H be the map that we talked about from a pre-sheaf to its sheafification, and then we want to. Here's what you want to do. You want to prove that any morphism F prime from F prime to G, where G is a sheaf, factors uniquely through H. uniquely through H. All right, meaning that it has to go like this. So anyway, basically what this is saying is that maps from the pre-sheaf to sheaves always factor through saying that they factor through the sheafification. So if you're interested in maps from pre-sheaves to sheaves, you could just as well work with sheafification. And then this uniqueness tells you that this is sort of the minimal thing that does the job. All right. So all right, I'll leave the rest of that as an exercise. All right, now that we have the idea of sheafification, we can do lots of definitions that we want to do. So the image of a morphism, the image sheaf, will be defined to be the sheafification of the image pre-sheaf that we talked about before, right? Remember, this one was defined as image prime f on U was just the image of right? And okay, and then of course we'll do the same thing for the tensor product. So f tensor with G will be defined to be the sheafification. So let me just abbreviate it because I want to write that out. The tensor product pre-sheaf that we talked about before, and of course on an open set U, that was just f of U tensor over OX of U of G of U. So we saw that pre-sheaf was not a sheaf, but without the prime, that'll be the sheafification of it. Okay, and then there's a couple more that we haven't mentioned yet that let's mention now. But actually, first we need some definitions. So let's say we say F is injective if its kernel sheaf is equal to the zero sheaf. Okay, and F is surjective if the image sheaf is isomorphic to G, right? So remember, F is a map from sheaves F to G. Okay, so let's see. Now remember, so if F is injective, then that means that F of U to G of U is injective. For all U. All right, remember we didn't have to sheafify for the kernel, so everything just works out very nicely. So if this is an injective map of modules, you can take the quotient module, right? You can take a G of U mod F of U, and let's try and define a pre-sheaf by that. The quotient of G and F on an open set U will just be defined to be a G of U mod out by F of U. Okay, and it turns out this is a pre-sheaf, so this gives you a pre-sheaf, and so then we take its sheafification. So G mod F is the sheafification of this thing. So if you like category theory, what we've basically done is we've made the category of sheaves on X into an abelian category. So in particular, now we can talk about exact sequences. So if you have a sequence of sheaves, so Fi going like this, this is I plus 2. All right, continuing. Maybe it ends somewhere, maybe it doesn't. But this is called this is an exact sequence if the image of fi is isomorphic to the kernel of fi plus 1. So the image of this map here should be equal to the kernel of this map here. This is the exact same definition you would have done for modules, but now the difference now is that we have to be a little bit more careful about the image sheaf and the kernel sheaf here. Or rather, we had to be careful about the image sheaf. The kernel sheaf worked out perfectly nicely. Okay, I've got one more for you. So the dual sheaf. So F dual is defined to be the sheafification of the sheaf that takes U to the OXU homomorphisms from F of U to OXU. All right, so if you want to take the dual of a module, you just take the homs from that module to the ring that you're the coefficient ring. Okay, but we're going to have to take the sheafification of that to get a sheaf. Okay, so that's the dual module. All right, we're going to talk more about this sort of abelian category structure for a minute here. Let me state this exercise that will be useful for us. It says that the kernel of a map of sheaves, if you take the stock at P, that will be isomorphic to the kernel of the induced map on stocks. So remember, the FP is the map, induced map on stocks from FP to GP. So this is a map of OXP modules, remember. Okay, so you can take the kernel of that map, or you could take the kernel of the kernel sheaf of F first, and then take the stock of that. And then this exercise says that you get the same thing. Okay, and the same thing works for the images. The stock of the image sheaf is the same as the image of the stock. Okay, so those are going to be nice results. Now we're going to use them in the following lemma. So in this lemma, let's take a sequence of sheaves. Fi plus 2, possibly infinite. Okay, and the three things, or we're going to have four things, so the following are equivalent. All right, the first one is the sequence is exact. Okay, and remember that means you know the image is isomorphic to the kernel at each step along the way. Okay, part B, restricted sequence. So Fi restricted to U is exact for all U open subsets of X. Okay, so you can check it by just checking every single open subset. Or in fact, you just need an open cover. So that Fi of, well, I better not use UI, let's do UK. So then the sequence is restricted to the open cover is exact. Okay, and then finally we have this one that says you can just check it on the stocks. So Fi P to Fi plus 1 is exact for all points of X. All right. Okay, so in some sense you can still check whether a sequence is exact locally. Let me not write down the proof. Maybe I'll just say it. Okay, well maybe I'll write it down. So the point is, in order for it to be exact, we need the kernel, or we need the. So A means that the kernel of Fi plus 1 is isomorphic to the kernel, the image of Fi. And then part D would just say that the kernel of Fi plus 1 P is isomorphic to the image of Fi P. But then by the exercise that I just talked about a minute ago, this is the same as kernel Fi plus 1 P isomorphic to image of Fi P. And then to see these two are equivalent, I think there's an exercise that we talked about last time. They said the sheaf isomorphisms are local. So if it's an isomorphism on every stock, then in fact it's an isomorphism. Okay, and then for B and C, the fact is that you can compute stocks locally. Right, it's good enough to know an open neighborhood of a point to compute the stock. So in that case, you can get B and C from D. Okay, so that's all I'm going to say about that. You can think more carefully about the details. Now, one thing that's not true. So here's your warning for the day. It is not true that the sections is exact. So let me write this. If we have an exact sequence, it may not be true that this thing is exact. Okay, and in fact, that's the whole problem that motivates cohomology, which hopefully we'll get to talk about a little bit soon. All right, let's do a couple examples to get us used to working with these definitions. So let's let x equal p1, and we'll take a point P in to be 1, 0 in D1. And we'll take the skyscraper, this is called the skyscraper sequence. Uh, 0 maps to OX minus 1, mapping to OX, mapping to KP, mapping to 0. All right, so this here is the twisting sheaf. This is the structure sheaf, or you can think of it as a twisting sheaf twisted by 0. And this here is the skyscraper sheaf with the field K concentrated at the point P. And so what is the map here? Let's have this map F is just going to be multiplication by x1. Okay, and so remember when we talked about the twisting sheaves, we said that there was maps if you multiply by a fixed polynomial, then you get a map from one twisting sheaf to the other with the twist increased by the degree of the polynomial. So look back at that if you don't remember that. And we're going to check that this is exact. So let's check this is exact. All right, so the first thing we need to check is that f is injective. If we have a phi as a section of OX minus 1 of U, so remember this is just a quotient of polynomials of degree minus 1, then if we take a phi times x1, this would be equal to 0 only if actually phi was equal to 0. Okay, so that shows that f is injective. All right, so that wasn't too bad. Now let's look at the image of f, or rather let's look at first the image, the pre-sheaf. This will just be equal to, well, functions of the form phi times x1, right? Where phi was a rational thing of a degree minus 1, and then you multiply by x1. But that, you can think about that for a minute. This is exactly just functions that vanish at p, right? And the good thing about this is that you can see this is a local condition to check whether a function vanishes at this fixed point p. You can check that on an open set. So this is actually the image sheaf. So in this case, the image pre-sheaf was already a sheaf, so we didn't need to sheaf of phi. Okay, and now let's think about this map G. What is this map G from OX to KP? G here is just the evaluation map that takes a regular function and evaluates it at P. So it's easy to see now so that the kernel of G is also equal to functions that vanish at P. All right, so we have the image of f is equal to the kernel of G here, so that gives us exactness in the middle. Okay, the last thing we need to check is that this is a surjective, or that G is surjective. Okay, but this is easy already, because even if you just take the constant functions, a constant function is a regular function, and even just taking those, that will map surjectively onto Kp. Remember, Kp is just the field K concentrated at the point P. Okay, so we've checked that this skyscraper sequence is exact. Now, I think in the next chapter, when we talk about quasi-coherent sheaves, we'll find even nicer ways to think about sequences like these to kind of convert them into commutative algebra that we're used to. But for now, I think this is a good practice to think about this. Okay, so that was example A. Let's now look at example B, which will just be a modification of example A. We're going to take 0, OX minus 2, and then we'll map by, this time, multiplication by x0, x1. So before, remember, our f was just multiplication by x1, but now we're going to multiply by x1, x2. So that's going to increase the degree by 2. So we'll go from OX minus 2 to OX. And then we'll have, again, the H will be the analog of G before. It'll be the evaluation map. This time at the 2 points, K plate P and KQ. Where here Q is the other point, 0, 1, and P is still 1, 0. Okay, this is exact. You can see it basically by the same reason as part A, and in fact, if you restrict, so if you restrict to UI, which is the set where xi is not equal to 0, then it exactly turns into part A, right? Okay, so I'll leave you to check that. But the interesting thing about this one is that it's not so H. So the point is H is surjective, but not surjective on global sections. All right, so what I mean by that, if you take OX of X, remember X is P1, so this is just isomorphic to the field of constants K. But then you have this map H into K plus KQ evaluated on the whole thing X, and this is isomorphic to K plus K. Okay, and H is just sort of the the diagonal map that takes A to A comma A, right? So this is so not surjective on sections. Okay, even though H was a surjective map, considered as a map of sheaves on sections, it's not. So this is supposed to give you an example of this warning here. That we had this exact sequence, but the sequence on sections was not exact. Okay. Okay, let's do another example that I kind of mentioned earlier. Now we're going to do it more carefully. So remember that when we have the twisting sheaves, you could define a map like this. So this is a tensor product over OPN of U, and you can map it into OPN of a D plus E of U. And okay, and this map is just sort of the obvious thing. You take a phi and a psi, and you map it to a phi times psi. So something of degree D times something of degree E. And these rational functions, you multiply them together, and you get to something of degree D plus C, and the denominators don't vanish on U. So that's all good. This defines, so this would give a pre-sheaf homomorphism. From OPN of D, the pre-sheaf tensor product, right? All right, because it's not, it's hard to check that this is compatible with restriction maps. Okay, but the point is now that this right here is a sheaf. So we had an exercise that I stated that was talking about the universal property of sheafification. It says if you have a map from a pre-sheaf to another sheaf, then it must factor through the sheafification. All right, so there's there exists a unique map here that makes this diagram commute. So we have a map from OPN of D tensor OPN of E into OPN of D plus C. So in fact, this is an isomorphism. So it is an isomorphism. So how are we going to see that? Well, recall from the last lecture, we had an isomorphism of OPN restricted to UI, where UI is the standard open subset where Xi doesn't vanish. This was mapping to OPN of D restricted to UI, and the point was you could just multiply by Xi to the D. And the reason this works is because on UI, Xi to the D is invertible, so you can just multiply by Xi to the minus Di to get the inverse, and this was an isomorphism. Okay, But let's put this all together with our tensor product. So if you take the tensor product, oh yes, let's go like this: OPN of E restricted to UI. And this map is multiplication by xi to the e. All right, so both of these maps are isomorphisms, so the tensor products should also be isomorphic. And then, we have the map that we're interested in right now, OPN of d plus e. And we also have, well, this is the same map that we're interested in over here, just with the special cases of 0. Okay, and what's this map here? This is just xi to the d plus e, and we know that's an isomorphism. So all these vertical maps are isomorphisms. But now we should look at this phi psi. How does this map work? It just maps to phi times psi, just a multiplication of the regular functions, right? And it's clear that this is an isomorphism, right? These are just right, for any open subset of UI, you just take the regular functions on UI, tensor them with the regular functions on UI over the regular functions on UI. I mean, it's just this, right? R tensor over R with R is isomorphic to R by this multiplication map. So that's okay. And then the point is, this diagram commutes. If we use this map that we were talking about. I think it's easy to check, see this commutes, right? And so that implies that this too must be an isomorphism, and that's what we wanted to. That's what we wanted to happen. Okay, great. So the result is that let me write the summary down here. OPN of D tensor OPN of E is isomorphic to OPN of D plus E. Okay, where we do have to take the actual tensor product with the sheafification. Remember our example earlier showed that if you just take the pre-sheaf version, then you don't get this isomorphism. All right, I think that's all I have to say about sheaves of modules in general. So in the next chapter, we'll specialize to quasi-coherent sheaves, which will be a class of sheaves that are particularly interesting in algebraic geometry.